Joe Ziegler with Amazon Web Services. We'll be starting here in just about 2 minutes. I just want to give a little time for anyone else who wants to sign into the webinar. So we'll get started here just shortly. Okay, everyone. I think we're ready to get started. Again, my name is Joe Ziegler. I'm a technical evangelist for Amazon Web Services. Thanks for joining us today. We're going to talk about building highly available, scalable web properties with AWS. You'll notice also you can ask us questions. There is a question, a little chat question area there in GoToMeeting. Feel free to ask us questions. We have a couple of other employees of AWS here online to help answer those questions. And I will try to address some verbally at the end. We most likely won't be able to get through all the questions, but we do have an email address that I'll show here that we can follow up with you if you have any left unanswered questions. All right, let's get started. So basically, what we're going to talk about is 5 principles for building highly scalable web properties. And these are actually the same 5 principles that Amazon used to develop its highly scalable infrastructure, and it's a lot of the different principles that we use when we design our services with Amazon Web Services. And that's elasticity, design for failure, loose coupling, security, and performance. So I'll go into each one of these. Number 1, elasticity. Elasticity is a fundamental property of the cloud. It's really the difference between when we talk about traditional IT infrastructure and the cloud. Now, the cornerstone of elasticity for Amazon is the EC2 instance. The EC2 instance is our Elastic Compute Cloud. Our Elastic Cloud Compute is basically it's your server processing instance, and it has the ability to scale up and down both vertically by creating larger instances and horizontally by adding more resources. Along with that, we've got CloudWatch. And CloudWatch is a resource for monitoring your EC2 instances as well as your other Amazon resources. Now that's going to work directly with EC2. And the reason that's important is we can use CloudWatch to auto-scale the EC2 instances. We can use metrics from CloudWatch, for example, high CPU use, to decide to automatically add new EC2 instances to our workforce. And that goes together with what we call auto-scaling, which allows you to scale up and down EC2 capacity. So for example, when you've got your website running on EC2, you can combine CloudWatch with auto-scaling to add new instances as the server load increases. Behind that, or in front of that, you can actually put your elastic load balancing, or the ELB. And this allows you to do network traffic distribution across your instances. Here's an example of how that would look. You would have your own website sitting with ELB, and behind that you've got your EC2 instance, which is using CloudWatch to auto-scale out. And this is how it would look in a real scenario with it working. Let's say at 6 a.m. your traffic is quite low, but throughout the day you get more traffic, and your EC2 instance is under more pressure to serve more and more content. Well, what will happen is that will trigger an alarm in CloudWatch, and CloudWatch will then initiate that alarm to auto-scaling, which will create new EC2 instances. Those instances will automatically join the Elastic Load Balancer, and the load balancer will now distribute that load across those instances. Perhaps later in the day, your load goes down. So an important part of the elasticity is not only being able to grow your server capacity, but returning that server capacity to AWS for cost savings. And in this case, as we have less traffic, we can scale down the EC2 instances and go back to one instance, thus saving cost. They automatically join the elastic load balancing groups, and they also automatically leave those groups, and the load balancer will take that into account. Elasticity is an extremely important fundamental part of cloud computing and building highly available applications. It allows you to really create adjustable capacity. Next design principle, design for failure. So our CTO is quite big on that, and he says everything fails all the time. And so what you need to be able to do in this scenario is design backwards. You should create your applications to continue to function even if the underlying physical hardware fails or is removed or replaced. In order to do that, you need to follow some steps. First, you should avoid single points of failure. So within your entire architecture, there should never be one particular system that, were it to fail, would take down your entire architecture. Assume that everything is going to fail and design backwards from that. So for example, I'll build a very simple, highly available web architecture here for you. So starting with a web server, we'll have a web server running on an Amazon EC2 instance. We're going to employ a service from Amazon, Amazon Relational Database Service, which is available as a hosted managed database service, either in MySQL, Oracle, or SQL Server flavors. So in this case, we'll have a very simple two-tiered architecture. Now, as it stands, this two-tiered architecture, of course, is not designed for failure. If either the database goes down or the web server goes down, essentially my entire site goes down. So we're going to employ some steps here. One step is we'll go ahead and attach an elastic IP. So that will be a public-facing IP that I'm pointing to my EC2 instance. Now the nice thing about that elastic IP is I could point that to other EC2 instances without it interrupting my traffic or affecting my end users. We can couple that with Amazon Route 53, which is our programmable domain name service. It's a highly available domain service that propagates very quickly throughout the internet, and you can programmatically change its settings. So what does this allow you to do? Well, in this case, we have mywebsite.com, and it's the DNS is being resolved by Amazon Route 53. It's resolving to an elastic IP, which is pointing to an EC2 instance and using RDS. Well, by using Route 53, I can make my website more highly available. Let's say, for example, I want to roll out a new version of my website, or perhaps I have a newer version of my web server. What I can do in that case is launch a new EC2 instance and use the elastic IP to point it towards a different EC2 instance where my users don't know that anything has actually changed in this case, so they're not directly affected to that. And that new EC2 instance can use my relational database. We can take that one step further and put these behind a load balancer. Well, that elastic load balancer is going to allow us to scale up. It's going to allow us to create new instances behind the scenes and be able to serve more customers. So if we have an event, for example, a very high server load or maybe slow response times, we can scale out. And as we auto-scale those up, those instances will join the workforce and they'll connect to RDS. If for something to happen to one of these instances, auto-scaling would automatically replace that instance with a new one. So now we've moved forward a little bit. We have a somewhat more highly available environment, but there's still a single point of failure. We don't have to worry about Elastic Load Balancer. That's managed by Amazon, and that already has a high amount of availability. We don't have to worry about Route 53. We don't have to worry about our EC2 instances because if something happened to one of them, they'll automatically get replaced, and we've got redundancy. But right now, were something to happen to RDS, our entire system would go down. So we've got a solution for that, and that's Amazon RDS multi-AZ deployment, or multi-AZ. In that environment, you can actually have an easy-to-create hot standby for RDS. And this is a simple setting that you actually do when you start the RDS service. This will create a synchronous replicated slave instance sitting in another availability zone. In the case that you've got a failure, where all your current applications are pointing to your master RDS, that master endpoint will then move automatically to the hot backup. Then in the background, you can bring up another standby and start that replication again. This helps you build a more highly available service. But what happens if something happens to availability zone A in this case? As you can see, all of our web servers are actually in A, and which is something, in the unlikely event something happened to that availability zone, we'd be down. Well, with auto-scaling, you can actually have it create EC2 instances across different availability zones. And the load balancer will also sit across those availability zones. In this case, were something to happen to either availability zone, the other availability zone would be able to grow and take up the traffic, thus keeping users up and not having any kind of downtime. You can tie this together using CloudWatch. CloudWatch has different types of alarms that you can set in order for you to know what's happening with your environment. In this case, we've got different metrics that we can look at. We can look at the server load, for example. We can take a look at the disk reads, the disk write ops, read ops. We can also look at the latency coming out of the web servers, for example. And you can tie those back into different alarms that can be raised either for auto-scaling, or they can be alarms that can reach out and alert you in case you're interested in finding out the status of your system. So in this case, I can actually send an email out. And then when everything returns to a state that's okay, I can also find out when that happened. There's a lot of different things that you can do within CloudWatch. You can monitor many of our different systems for that. You can set different types of notifications to find out what's happening. And then if you want to, you can tie these back into auto-scaling. So you can actually tailor your auto-scaling to exactly what you want. For example, you can tailor auto-scaling to be time-based, in which case you could turn down servers if you know that your load's going to go down maybe after 5 o'clock on Friday. Or you can say, well, if I have a high aggregate CPU utilization, for example, if the aggregate of all my CPUs is over 80%, I want you to scale up more servers. And if it drops below 50%, I want you to scale them back down. So I want to talk about some of the AWS building blocks. We really have two kinds of different services that are running in AWS. We have some that are inherently fault tolerant, and those are usually associated with a region. So for example, you can launch an S3 bucket, and you can pick which region you want that bucket to be in. And for S3, you're dealing with it's 11 nines of durability, which means you can actually put 1 million objects in S3, and over a period of about 100,000 years, you could lose one object. So it's quite durable. So everything that runs in a region is benefiting automatically from the multiple availability zones that are part of that region. S3 is automatically replicating between those zones, for example. Route 53 is available because it's able to run across those different availability zones. So anything that you see over here on the left here, the fault-tolerant services, you can assume that they're already highly available. On the other side, we do have services that are fault-tolerant, but you really have to architect and use those services correctly in order to get the full benefits of fault tolerance. And that's really the EC2 instances, RDS, and virtual private cloud. So I want to talk about one of our customers who has successfully really engineered a highly available service. And that's Netflix. Netflix right now it's an online streaming service used exclusively in the US. They actually make up 25% of the internet traffic in America at their peak. And now they're the #1 cable provider in America. Netflix builds its architecture around the concept that everything fails. And they've actually done it in a very unique way. They've created something called Chaos Monkey. Chaos Monkey and the Simian Army. What Chaos Monkey does is it actually goes through their entire architecture and it randomly fails different parts. So it will turn off EC2 instances, for example. It will make the database go offline, depending on what level of pain that they want the monkey to actually induce. This monkey is actually running all the time within Netflix. And so they have actually built their entire architecture to take that into account. They assume that the EC2 instances will be taken offline. They have to have a highly available database behind it. So I encourage you to check out Chaos Monkey. It has been made open source. It's part of the Simian Army. I think if you Google for that, you should be able to find everything about it. So let's move on to another design principle. and that is loose coupling. You want to build loosely coupled systems. This is going to allow you to scale everything up. A loosely coupled system basically means you have very clean interfaces between your different services, and these interfaces should be able to scale. You should be able to create independent components. So basically, every component does one type of job, one service, right? You should be able to design everything as a black box. You have a clear interface between these different levels of services. One service doesn't need to know how another service functions internally, and doesn't have any dependency on how that functions. It only knows that it has this types of inputs and these types of outputs. This will move you towards thinking of more of a service-oriented architecture. And this is the kind of architecture that is going to be able to scale and be highly available, because you're going to have many of these services running. And if one service takes a long time, you'll be able to start more of these services. So let's look at an example for that. Let's say we have a very simple video encoding service. Something like one of our customers is Vimeo. And Vimeo allows you to upload movies, and they will transcode those movies and they'll publish it on their website. If you were to build an architecture like this, where you've got two services that are tightly coupled, as you upload that video file, you would have a dependency on the transcode and publish step. Were something to happen to that transcode and publish step, your architecture perhaps would not even allow you to receive a file. Additionally, what happens when you receive a lot of files, or if you can upload files faster than you can transcode and publish? You need a way to decouple these services. One way you can do that is using a queue. A queue will allow the receive service to continue to receive files and then add jobs to the transcode and publish service. So let's take a look at how that would look in our architecture. So in this case, I'm going to use something called Elastic Beanstalk. And Elastic Beanstalk is a container service from Amazon. It allows you to run Java, PHP, and ASP.NET apps in a managed environment, which means we scale them up for you. We handle the connection to the load balancer. We do all those settings for the auto-scale environment I had talked about earlier. However, you can still go under the hood and decide how those settings work. You can still see your EC2 instances getting launched. Now we're going to go ahead and use that web app. And to store these files that we're uploading, I'm going to use Amazon S3. Now S3, as I said before, is highly available. Excuse me. S3 is actually, it's very highly available. In fact, at this point right now, it's handling about 750,000 requests per second. So it's a really great environment for us to be able to use for storage for these uploading of these files. So we'll connect Elastic Beanstalk to that. Now for the queuing, I'm going to use Amazon Simple Queue Service, or SQS. That is also a highly available service. It has a web endpoint that you can connect your application to. And we can connect these together. So as you upload the file, what's going to happen in this case is I'm going to grab the file, my Elastic Beanstalk app, I'm going to place that file into S3, and then I'm going to queue up a job. And I'm going to say, hey, look, here's a file I needed to be transcoded. Now what I can do in this case is I can put my transcoders and connect it to that job queue, and those transcoders, they can auto-scale. So as we upload more files, perhaps that job queue is growing. Well, guess what? I can actually connect auto-scale to the job queue, and I can say, for example, for every 100 jobs, I want you to kick off another EC2 instance. This means that these two jobs now can scale independently, and I get the benefits of loose coupling. As these guys kick off, they can go to S3, and they can pull down that file. And we don't have to worry about S3 scaling, because as we said before, it's handling many, many requests worldwide right now. So this is a very simple workflow. But what happens if we want to get a slightly more complex workflow for our web app? So we'll take a look at something like this. We want to go ahead and have people upload the video, and we're going to check the video. And maybe, let's say, we're offering like a freemium type service. If the video is too long, we want to shorten the video. If it's not too long, or after we shorten the video, we want to check to make sure it's really a legitimate video. So we're going to do a little bit of a decision process here. If it looks like it's spam, we're going to reject it, and we're going to end the workflow. If it's not spam, then we'll go ahead and transcode it, and then we'll publish and notify our customer. So how is that going to look in the web architecture using the queuing services and adopting those loosely coupled principles? So this is what we kind of started from. This is a very simple workflow. This is basically not checking to see if it's spam, not checking to see if the video is too long, and taking everything in and just automatically transcoding it. And this will scale, and it's highly available, but it doesn't really meet our total business need. So what would the architecture look like if we wanted to include this more complex workflow? So here's one way it would look. And I know there's lots of squares there, and we'll just kind of go through this really quick. So basically what would happen in this case is the entry point into our business app is we upload a file. The file would automatically go to S3, and Elastic Beanstalk would put a job into the SQS to say, hey, I want you to check this video. Then we've got an auto-scaling group of EC2 instances whose only job it's going to be is to check the video. It's going to check the video, and it's going to do one of two things. It's either going to say, hey, you need to be resized and create a resizing job, or hey, I need you to be checked for spam. And you can see the decision trees are following that original logic, and it's going through queues at every layer. Now, we can scale up quite well in this case. If we lose an EC2 instance, people are still uploading files. In fact, we could lose the whole back end of our system, and customers wouldn't actually know that other than that their files would be ready a bit later. There are some problems with this type of architecture, though. Well, first of all, it's kind of hard to maintain. We've actually hard-coded in a bunch of the workflow logic into the architecture. It's also really hard to audit. Well, what happens when there's an error somewhere in the way? How do we find out that something's stuck in transcoding, for example? How do we find out that a lot of more files are spam than aren't spam? What happens when I have to change this workflow? I'm going to have to completely change my architecture. I'm going to have to add new EC2 instances connected into new SQS queues in order to facilitate any kind of changes into that decision process. And it's really quite low-level architecture if you look at it. So what is it that we're actually trying to do? So here's that workflow. We've got kind of two components to this workflow if we look at it, right? We've got activities and steps, right? So this is the actual work, right? Check the video, shorten the video, check for spam, reject, transcode, publish, and notify. And then we basically have a couple of decisions that are involved in that, right? So we can break this down into a couple of things. We can break this down into tasks, decisions, and history. So we're really focusing here on what our business workflow is, not so much on the actual implementation, not so much on the architectural design for the workflow. This is good because we can build stateless systems this way. And stateless systems are fundamental to being able to scale out horizontally. And horizontal scaling is really one of the benefits that the cloud brings to you because we can use that auto-scaling feature. We can kick off new EC2 instances which can bootstrap, connect to the load balancer, connect to the queues, and perform business processes. It also means that it makes us more highly available because if a machine drops off, because it has no state, we can add another machine to join back into the pool without it damaging our workflow. So we do have a service for this. It's called Amazon Simple Workflow, and it allows you to create scalable, resilient applications without having to focus in so much on building an architecture that closely matches that workflow. Now, SWF keeps track of the state for you. It'll keep track of the executed tasks, timeouts, and errors. It's made of a couple of components. Fundamentally, you have the actual simple workflow service, and you can assume that's highly available just like our other services that I mentioned earlier. And within that, you've got the SWF worker and the SWF decider. So if we went back to our actual workflow, you can see where these would fit in. We would have an SWF worker, for example, to do the transcoding, and a decider to decide whether something's too long or too short, or whether it's spam. So the deciders, they do the coordination logic. And what they do is they work on something we call long polling. Basically what happens is the decider will connect to Simple Workflow Service, and it will poll, and we'll hold that service for up to 60 seconds to tell it whether it has something to do. This means that you don't have to have a lot of complex polling logic. It'll evaluate the workflow, and it'll keep the execution history in a JSON format. And that execution history is going to allow us to build really complex workflow items, and it's also going to make it so that everything's auditable. and then it will return the decision to SWF. So SWF itself is the coordinator. You'd have the decider pull up a job, decide what the next course of action is, and then return that next course of action into SWF. And then it continues to loop on that over and over again. Now, you can actually write the workers and deciders in the SWF SDK, which we have for .NET, Java, and PHP, or you can call the API directly. Then we've got workers. Now, workers are the ones that are actually doing the tasks. Very similar environment. They'll be polling, and they'll execute a task and send heartbeats back to SWF. Basically, you'll have two outcomes from that task. You'll have a success or a failure. And just like the decider, it's going to continue to do this in a looping fashion. So how will that architecture kind of look? Well, in this case, for Elastic Beanstalk, what we'll do is have it communicate directly with Simple Workflow once a file is uploaded. Simple Workflow will then manage EC2 instances as either SWF workers or SWF deciders as needed for the actual workflow. You can add more of those to scale out. What's nice is those patterns we just covered previously, they absolutely apply for Simple Workflow in this particular project. So in this case, for example, if it turns out we have a lot of transcoding to do, we can auto-scale out those EC2 SWF workers. And in fact, if we have a lot of files coming in, we can also scale out those deciders. But what about high availability? Well, just like before, we can scale these services across availability zones, just in case in some unlikely event, one of those availability zones was affected by some kind of event. We can also reach out to on-premise. So if you've got, for example, workers running in your own corporate data center, you can still coordinate through Simple Workflow Service. You can also use not only on-demand instances, but you can also use spot instances. A very good case study for that, of course, is Vimeo again, where they've got a freemium model and a freemium model and a paid model. If you go with the free model, you upload your file, it usually gets transcoded and is available within 24 hours. If you go for the pay model, it's usually transcoded immediately and available in about under an hour. And the way that they do that is if you're not paying, they actually use spot instances on the back end. And those spot instances may be available, they may not be available, but that way they can actually cut down their costs. So what is this going to look like? So here's our original transcoding architecture. Fairly complex, still highly available, still scales up as we need it, but pretty much hard-coded to what our business logic is. So how will this look with Simple Workflow? There we go. A much more simple architecture to deal with. We have Simple Workflow running in the middle there. We're still storing our files to S3, but we let Simple Workflow manage our workers and our deciders. And we're still highly available. We're scaling up. But when we want to change our business logic, we can work with the Simple Workflow service instead of reconfiguring our entire architecture. And this creates love because you have no new languages to learn. Your code's going to work just like it did before. You do need to program Simple Workflow itself with a Java library, but everything else that you want to write, you can use in any language you want and run those within EC2 instances. We have a full API available for this. It's actually quite easy to use. I encourage you to take a look at it. So you can see we actually have two services here available. Simple Workflow Service and SQS. And SQS has actually been around in some of the earlier days with Amazon Web Services. And Simple Workflow, this is a newer one that we've recently launched. And so you can kind of ask yourself, well, is there a bit of overlap there? And there is, actually. Because before Simple Workflow Service, people would actually create these complex workflows using SQS or using their own queuing service. So as a rule of thumb, if you have a very simple chain tasks without any kind of complex decision, SQS is a really good way to create a loosely coupled, highly scalable environment. However, if you've got tasks with a decision graph attached to it, then we would recommend using Amazon SWF. It will just manage your services a lot easier. It will create a simpler architecture, and you'll still meet all of our design principles when you use it. Okay, so now I'm going to move on to security. So fundamental to AWS is the Identity and Access Management, or IAM, service. This functions very much in a similar environment that most people are used to by having groups and users and roles. And you can assign very granular permissions to these different users and to these different roles. And you can also make these users do not necessarily have to be people. They can be applications, for example. So in my own architectures, when I design a continuous integration environment, the continuous integration server itself actually runs as a particular user that I have very strict permissions attached to. We also support multi-factor authentication. In this case, you can use, for example, you can buy a Gemalto token. I believe they're about $9 or $10 that you can order from us. Or you can even use Google Authenticator, and you can use a virtual multi-factor authentication. And this can not only be used to log into your web console, you can also use it in your business logic. For example, you can require multi-factor authentication before you allow it to delete from an S3 bucket. Or you can actually interface with multi-factor authentication via our APIs. So what you can do with the security groups is really create complex layered security. Take, for example, if we have this type of architecture. We've got an end user. You've got a load balancer, several layers of EC2 instances. So you've got basically here an end-tiered architecture. Now, kind of in the traditional IT world, what you would end up doing in the case is you'd set up a DMZ. You would have a certain level of access on one side of the DMZ. You'd have some file servers within the DMZ, and then you'd probably have your databases behind both sets of firewalls. Well, this is actually a lot easier to do with security groups. What you can do is set up each tier of your architecture into different security groups and have different types of rules on these security groups. So for example, at the front end, we can have rules that only allow port 80 or port 44 or 443 connections from the outside world. And then at the next level, perhaps we only allow connections from web servers given their security groups or their IP addresses. Maybe we only let them on a certain port. Additionally, you have the same type of layer on the database server. Web servers are able to talk to application servers, and so on. This allows you to create extremely secure layered environments. We have several certification alliances. We operate the same cybersecurity funded traditional data centers. We also have several different organizations that have sold us report to them. For example, our ISO 27001 meets our main Oxley. You've got compliance, FISMA compliance, GovCloud. Additionally, we're PCI DSS compliant. So that means I can actually process all your credit card transactions through EC2. Amazon.com uses process all their actual credit card transactions. You can imagine quite concerned with their security. So we meet all the levels of clients need to meet in order to serve that customer base. Okay, let's move on a little bit. I'm going to move on to performance. How can you actually increase your performance, take advantage of AWS services? At a very basic scale, you can do, very basic bit, you can do vertical scaling. And what is vertical scaling? Well, that tends to mean that you've got a large monolithic application, and the only way that you can scale it up is to add more horsepower to it. So, for example, you've got a database server, you're running it on a smaller instance. With AWS, of course, what you can do is you can stop that instance and you can create a larger instance and run that database and kick that database back on and immediately scale that up vertically, right? And we have lots of different flavors that you can use in order to do this scaling. We've got high memory instances, high CPU instances, cluster compute instances. We can actually use graphical processing units depending on what your workload is. We recently have added high I/O instances that you can use. For example, you can actually create a cluster compute 8 extra large instance, 60.5 gigabytes of memory with 3.3 terabytes of storage. Or if you need to use GPU, you can actually do a quadruple extra large GPU instance. And we continuously are adding more instances based on feedback from our customers. Another way in order to gain performance is Amazon ELASTICACHE. And that is a Memcached compatible in-memory cache system that we manage for you. So if you've ever used Memcached, it's very simple to switch over and start using Amazon ELASTICACHE. How does that work? Well, typically what you'll find is that people like to put the in-memory caching layer between the database and the web server and cache those results. So if you've got a database that's heavy on the read side, you can use ELASTICACHE and it'll automatically manage the nodes for you to pull out the information from the database server and save that into cache. It'll depend on what kind of framework you're using and what kind of technology stack. I have built systems using Python and Django, for example, and there was plugins that immediately just started working and started caching the database with very minimal effort. But it's going to depend on what your architecture is like and the technology stack that you're actually using. Search engines. Now, I've actually had to implement architectures using search engines before, and I can tell you search engines are hard. I've worked with technology that I find myself spending a lot more time scaling up search engines and keeping them up and running as opposed to creating value for my customers. And so we've actually got a managed search engine service available. And what do you know? It actually comes from Amazon. It's a search engine that they have used, and we have turned that into a service available to anybody. And it has several features. For example, it can do relevance and ranking for you. It can do faceting. So if you want to be able to drill down on the different searches, you can do that. It allows you to do range searches. And the name of it is Amazon Cloud Search, and it's a fully managed search service available from us. It's built originally on the A9 search technology that Amazon.com uses. And what it really does is it brings this very complex problem down and makes it so that anybody can actually use it. And we will automatically scale you up. And we can actually take in as much traffic as you want, we can take as much data as you want, and handle as many searches as you want. And we will scale that out for you in the back end, and you don't have to focus in on that. So that gets rid of that undifferentiated heavy lifting that we talk about a lot at Amazon, and allows you to focus on using that search and not actually building services to manage that search. And this is what it looks like. It's basically got two endpoints. It's got an endpoint that connects actually into your documents on what you want searched, and then it provides a search endpoint that your application would use in order to reach out and query and request the search. As your traffic grows, we're able to partition that traffic across different instances running in the background. So you basically have two types of growth that you're going to find in search. And that's going to be the quantity and the size of the document data, and then the actual search requests in terms of volume and complexity. We're able to scale across both these different types of growth. So what would that look like in our web architecture? Well, again, we're going to have our auto-scaling group here. And I'm not showing it here, but this would go across availability zones, for example. We've got our RDS running with a read replica ready as a hot standby. And we can include Amazon Cloud Search. And Cloud Search, just like many of our different services, is highly available. And we'll connect that endpoint into the databases to actually do the indexing. And the search endpoint is available to the EC2 instances. So we brought together many different concepts here. Let me show you what it would look like in a slightly more complex media sharing architecture. So I'm going to start with this guy. It's actually quite big. But when we break it down into the components, you can see how it works. So let me clean this up. Here we go. So here's our media sharing reference architecture. Let's take a look at what's going on in this. And it's got a couple of services that I didn't go into great depth about. So first of all, on the very front end, we're going to have Route 53. And Route 53 is going to allow us to programmatically change our DNS whenever we need, which means I could potentially point our entire website to a different infrastructure. Now, Route 53 also has latency-based routing. That means if I wanted to, I could have this type of infrastructure sitting in different regions across the world. And that way, customers that are coming in from, let's say, Japan, for example, would be shuttled to the services that are running in the Tokyo region. So let's go behind that. And we've got several elastic load balancers running here. So first of all, Perhaps we've got some auto-scaling going on the web server side. And these web servers are they're serving different requests. People are asking for their media files. We've got a content delivery network here in the middle. That's Amazon CloudFront. That is our CDN, Content Delivery Network. And right now we've got over 33 points of presence available on that network. And I'm happy to say we just recently opened that point of presence that we're serving CloudFront out of Sydney right now. So for my Australian friends, I think you'll find that quite useful. In this case, CloudFront is using S3 as its origin. So that means any content that's placed in S3 is going to be distributed around the world via CloudFront. And then we've got our upload servers that are also sitting behind an elastic load balancer. And these will all scale up as required. And they're going to connect into S3 to pull down data and to do transcoding. And maybe we have a very simple workflow. And so in this case, we're just going to use SQS. And we're going to have different types of instances connected to SQS to pull out the media files for types of processing. And in the back end there, you can see there where that number 4 is, we actually have 2 different kinds of instances. We probably have some core instances that are auto-scaling out that are either reserved instances, meaning I pay for these instances and I'm going to use these instances all the time, or on-demand instances. And then we're going to enhance our working farm by including spot instances. And that's going to save us some costs. That means we can use probably less of the on-demand instances when those spot instances are available. In the back end, we can have our data store, our highly available RDS, and then we'll plug in Cloud Search there in the back. And this is your overall architecture. I'll just leave that up there so you can take a look at it a little bit longer. Okay. So we talked about really 5 of the main principles. We talked about elasticity, right? We can ask the cloud for as much server capacity as we want, and we can return that capacity to the cloud as needed. But in order to be able to use that elasticity, we really have to create applications that are able to scale out horizontally. And that usually means that our applications that are stateless, and that as we add more servers, we can basically service more customers. We talked about design for failure, right? Great reference from Netflix, by the way. You can find a lot of information about their architecture. They have published white papers about it. You can see how they designed from day 1 for failure. And feel free to grab Chaos Monkey and try it out for yourself. We talked about loose coupling of the architecture, right? So that is going to allow you to actually gain elasticity throughout your entire architecture. On every tier, you're going to be able to scale up as the workflow is required and scale down. Plus, it means you're going to be more highly available. If something happens to one of those back tiers, as that front tier is still able to accept orders, for example, you can ramp up the back tier if orders start backing up, and you can scale out that way. We talked a bit about security. So you can use security groups to create multi-layers of security throughout your architecture. And we talked about performance, different ways that you can increase performance. So for example, vertical scaling, you can add bigger instances. We talked about horizontal scaling. You can add Elasticache into your architecture in order to improve database performance. And then you can also use some of our services which scale out and have consistent performance, for example, Cloud Search. And this together will help you to actually get up and get running quite quickly. So you want to get that first version up as quickly as possible. So, well, we're just wrapping up here. I'm going to go through and try to answer some questions. I just want to let you know that if I'm not able to get to your questions, you can email them here and we'll try to get hold of you. Oh, I almost forgot. For my Australian customers, I think probably you might be interested in a little bit of an announcement that we have coming up. And we've got an ANZ Customer Appreciation Day coming in November, and that will be in Sydney, so I hope to see everyone there. Okay, well, let's go to some questions. Okay, here we go. First question I have, can ELB be used to scale up a set number of EC2 instances? ELB itself is not actually scaling up. It works in conjunction with auto-scaling. And with auto-scaling, what you can do is you have different parameters that you can work with. One of those parameters is going to be the reason that it actually does the auto-scaling. So in this case, you could do like high CPU. But a couple of the other parameters that you use is a minimum number and a maximum number of EC2 instances that you want. So for example, you could tell it you always want it to run 4 instances. Or sometimes we have customers who want to have one instance always running, and they want to ensure that if something happens to that instance, if it fails over, it'll get restarted. In that case, they use auto-scaling with kind of a floor and a ceiling set to 1. So the answer is yes, it can. You can also do it on time base, for example. You can say, if you want to, you can have 5 instances that are running over the weekend, and perhaps before people come in for work Monday morning, you scale it up to 10 more instances. How are blob databases handled in Amazon? Well, our relational database service they're fully featured MySQL, SQL Server, and Oracle databases. And so they're going to handle blobs exactly the way that those vendors have designed the databases to handle the blobs. Additionally, we do have NoSQL databases. The NoSQL databases are going to store everything as Unicode. And so you can't really store a high level of binary data in it. Most customers are going to probably combine the database with using our object store S3 for blob data, because S3 is highly available and it has a great degree of performance and it can scale across so many requests. Sometimes it makes more sense to have a key in the database and then to go back to S3 in order to pull out that binary data. Let's see. Does Amazon DynamoDB have restrictions on the packet size? So underneath all of our services, there are still web services, and so we are restricted by the HTTP protocols for the puts and the gets, and that will include Amazon DynamoDB. And I don't have on the tip of my tongue what the exact size is, but that's something I can follow up and find out. But yes, there are restrictions on how much you can do in a particular put and a get. Any plans to support Rails and Beanstalk? I would love to be able to address that question. We've got basically Beanstalk, really good for PHP, Java, and .NET. Obviously, it does not right now have support for Python or for Ruby, but we have a lot of customers who ask for that. So I would just say, stay tuned for that. Multiple IPs for a single EC2 instance seems to only be supported in VPC. When will it be supported in standard EC2 instances? I do not know what our approach is on that right now. I'm going to need to follow up on that one. Within, of course, VPC, you can now add a couple of hundred of IP addresses to an EC2 instance, but with the Elastic IP, you can't. So, Simon, thank you for asking about that one. I will need to follow up on that and to see what we are doing about that. Let's see. How does the master-slave RDS work internally? So what's happening with when you do a multi-AZ RDS instance is you'll go to your original instance, and you can actually click this option that say, hey, make this a multi-AZ RDS instance. And it will back itself up, and it'll take a few minutes to do this. But what will happen is you're actually going to be charged for 2 underlying EC2 instances, and what's going to happen underneath it is that master instance is going to synchronously send out and do copies of that data in a synchronous manner. So you're guaranteed that the transactions are going across those 2 instances. Were there anything to happen to that master instance, what happens is that endpoint will fail over. So that endpoint you're using for your database will fail over and point to the slave instance. And that slave instance will become live. Now that failover process will actually take a little bit of time. So you will have downtime while that's happening, and you'll have to build your application to kind of deal with that. But it'll be minimal downtime, especially compared to actually losing your master database. Well, those are all the questions that I had. I think we're going to go ahead and wrap up now. I appreciate everyone dialing in and listening to me drone on here for a few minutes. If you've got questions that we didn't get answered, again, let me just put up the slide. Let's see. We'll just go over here. send your questions here, and we'll follow up with you. And again, just want to remind you that if you are in Australia, please feel free to learn about our Appreciation Day. This is the hashtag. We'll have that updated with information as it comes available. And thanks again.